Good afternoon, friends, and welcome again to another maths class of Parijat sir classes. And today we are going to discuss another topic of mathematics of class 12, and that is called the differentiability of a function. The differentiability of a function. We will be learning this chapter today, and you are watching Parijat sir classes. So it is my request to you, please like, share and subscribe it as much as possible so that it reaches out to each and every student of those who are attempting the board examinations for the 23-24 session. For the 23-24 session, those who are attempting it, and also maybe for the next all the board exams which will be coming. This is completing the full syllabus of any board exam, mind it. This is for the any board exams, for any entrance exams, for any entrance exams. So I would request you, please share it as much as possible so that it is beneficiary to all those students, those who are not able to get proper guidance. Okay, so without wasting any time further, let us get started with the topic differentiability of a function. So first of all, friends, see what is the definition of differentiability. Let fx be a real valued function. That means you have a function which will be called as fx, defined in an open interval. That means they will ask you to check within this interval, and let you choose any value c, which is, suppose a is 2 to 5 and c is a value, suppose 3. Okay, so fx is said to be differentiable at x if I want to check that a function is differentiable in a value which is between the two limits. Then what is the format of writing the function's differentiability? This is the format of writing the differentiability. Limit x tends to c, fx minus fc by x minus c. It should exist infinitely. It should exist infinitely. That means you are choosing a value 3 which is between 2 and 5, and the function should exist at that value, at that particular value. It should exist. And how to check it? This is the formula for checking the differentiability. Okay, so let us see that how it exists. And please note one more important point, that is, a function is differentiable at a point. If it is differentiable, it is necessarily continuous. Mind it, it should be continuous, but the converse is not true. That means if it is continuous, it is differentiable may not be true. But if it is differentiable, it has to be continuous. It has to be continuous. The function has to be continuous. Okay, so let us start with the function fx equal to mod of x, and let us check it at x equal to 0 whether it is differentiable or not. Okay, so let us check. We know that if x is less than 0, the function will be taken as minus x, and if x is greater than 0, the function will be taken as plus x. Clear? So let us now, using this part, so let us check the differentiability. So we are testing first we are testing the left hand derivative at x equal to 0. So please see how to write it. The left hand derivative, how to write a left hand derivative at that point. So it is limit x tends to 0 minus. Okay, so it is limit x tends to 0 minus. If you are checking at 0, it is 0 minus. And how to check the right hand derivative at x equal to 0. How to test it? This is the way to write it. This is the way to write. Limit x tends to 0 plus, limit x tends to 0 plus fx minus f0 by x minus 0, because it is fx, it is limit x tends to c fx minus fc by x minus c. So if I am testing at 0, I would write limit x tends to 0 minus or 0 plus fx minus f0 by x minus 0. This is how I will write it. So let's now check the differentiability. Okay, so limit x tends to 0 minus can be written as limit h tends to 0. Please note that. And x is written as 0 minus h because it is less than 0 minus. It is 0 minus, so we'll write in place of x I will write 0 minus h minus f0. So in place of x I will write 0 minus h. That means it is f minus h minus f0 by minus h. So in place of x I will put minus h. In place of x I will put minus h. So minus h mod of minus h is h, okay, by minus h, which is minus 1. It is coming minus 1. Similarly, right hand limit, it is 0 plus, so I will write 0 plus h, okay, f0 plus h minus f0 by, in place of x I am writing 0 plus h. So if it is fh minus f0 by h, so in place of x I will put h. In place of my function mod x, in place of my function mod x I will put h minus 0 by h. So mod h is h, so h by h is cutting and it is giving 1. So watch, left hand derivative is not equal to the right hand derivative at x equal to 0, and we will write it is not differentiable at x equal to 0. Okay, so please watch it. The left hand derivative and the right hand derivative has to match, then only it will be called as a differentiable function. It will be called as a differentiable function. Clear? Let's see more and more examples. Okay, now see, this is the function. For x less than 2 I will choose this function. For x equal to or greater than 2 I will choose this function, and I have to test the differentiability at x equal to 2. So first I will take the left hand derivative at x equal to 2. So I will write limit, I will write this limit x tends to 2 minus fx minus f2 by x minus 2. This is how I will write. Okay, so then I will write h tends to 0, and in place of x I will write 2 minus h minus f2 by 2 minus h. In place of x, in place of x I will put 2 minus h because it is less than 2. So I have taken as 2 minus h. So h tends to 0. Okay, so in place of x I will, so I am testing less than 2, that means I will choose this function, and in place of x I will put 2 minus h. So here it is 2 minus h minus 1, and f2, that means in place of x I will put 2, so it is 2 minus 1. So this comes out to be this, and in place of x I will put 2 minus h. So answer is coming, the left hand derivative is coming 1. Similarly, for the right hand derivative, this is how we will write limit x tends to 2 plus, limit x tends to 2 plus. I will write it as limit x tends to 2 plus. Okay, and see how to write this. So h tends to 0, in place of x I will write 2 plus h, and I will choose this function. In place of x I will write 2 plus h. So this is 2x minus 3, and in place of x it is f2. That means in place of x I will put 2. So the calculation comes out to be this. h cuts, it is 2. So now see, left hand derivative came 1, right hand derivative came 2. So these are not equal. That means it is not differentiable at x equal to 2. It is not differentiable at x equal to 2. Clear? Let's see the next function. We'll check the next function. This is our function x square. Our function is x square sine 1 by x if x is not equal to 0. That means less than 0 or greater than 0, I will choose this function. And I have to test the differentiability at x equal to 0. So let's check. So this is how I will write it. The left hand derivative, limit x tends to 0 minus, because I am testing at 0. So in place of x I will put 0 minus h. So h tends to 0, that is 0 minus h minus h0. In place of x I will put 0 minus h, which is minus h. Now less than 0 is this function. Okay, so here I am putting, in place of x I will put minus h. So this is this. So there is a minus h. Please watch. If I put 0 here, that means it is a 0 into, please watch, this is an oscillating function between minus 1 and plus 1. So this is minus 1 and this is plus 1. So this is an oscillating function between minus 1 and plus 1 into 0. That means the answer will come 0. Similarly, if I test the limit at x equal to 0, the right hand derivative is written like this. The right hand derivative is written like this. So in place of x I will put x plus h. In place of x I will put x, because I have to test at 0 plus. 0 plus, so I will put 0 plus h in place of x. So it becomes this, and because it is more than 0, so I will again choose this function. So in place of x I will put h. Okay, so 1h will cut out from here. It is this. So now if I replace h with 0, so it is a 0 and an oscillating function between minus 1 and plus 1. So the answer is always 0. So I can see that the left hand derivative is coming equal to the right hand derivative, and so it is differentiable at x equal to 0. It is differentiable at x equal to 0. Okay, so what is the value of that differentiability at 0? Remember it. What the answer is coming? The left hand derivative and the right hand derivative, that is the answer of the differentiation of the function at x equal to 0. That is the answer of the differentiation of the function at x equal to 0. Is the same answer as the right hand derivative or left hand derivative. Clear? Next, see the next function. So this is our function and I have to test it, the differentiability at x equal to 1. So first of all, the left hand derivative at x equal to 1. So limit x tends to 1 minus. Limit x tends to 1 minus fx minus f1 by x minus 1. This is the limit at x tends to 1 minus. X tends to 1 minus. So I will take, in place of x I will put 1 minus h. So limit h tends to 0, 1 minus h. Here is 1 minus h. So in place of x I will put 1 minus h square minus f1 square. What is f1? F1, in place of x I will put 1, so it's 1 square, and this comes out to be this. Now a minus b whole square is this, and this cuts. So taking a h common, this h and h cuts, so it is coming as h minus 2 by minus 1. Now putting the value of h as 0, we get minus 2 by minus 1, which is coming at 2, okay. So now let us see the function at the right hand derivative. Let us see the right hand derivative. So this is how you write the right hand derivative. Clear? So in this case, and we are checking at 1, that means I will check at limit x tends to 1 plus. So h tends to 0, limit h tends to 0, and x, in place of x I will put 1 plus h minus f1 by 1 plus h. So in place of x I will put 1 plus h, and in place of x I will put 1. So solving this, we get this 2. That means we see that the left hand derivative is equal to the right hand derivative at x equal to 1. So it is differentiable at x equal to 1. And what is the value of that function, of that differentiation at x equal to 1? It is the value of the right hand derivative or the left hand derivative. Or the left hand derivative value, okay. The value of the function, the value of the differentiation at x equal to 1 is actually the value of the left hand derivative or the right hand derivative. So let's see the next function. This is our next function, fx equal to e to the power x 1 by mod x minus plus this. So this is applicable only when x is either greater than 0 or x is less than 0, and at x equal to 0 I will choose this value. So we have to test the differentiability at x equal to 0. So let's check. First of all, we will write the left hand derivative at x equal to 0. So limit x tends to 0 minus, so in place of x I will put 0 minus h. In place of x I will put 0 minus h. Okay, so it is less than 0, so I will choose this function, and in place of x I will put 0 minus h. Okay, so 0 minus h is actually minus h. So here is, see, we are putting in place of x minus h. Mod of minus h is plus h. Okay, plus h. So this part fully cancels. It is e to the power 0, which is coming as 1. Okay, and h also cancels 1. So left hand derivative is coming 1. Now let us check the right hand derivative. So this is the right hand derivative. This is the right hand derivative of the functions. Okay, so here we see that we have to test it at more than 0, so 0 plus. So in place of x I will put, is 0 plus h. In place of x I will put 0 plus h. Okay, so let's see this. So from here we can see that in place of x I will put 0 plus h. So here we put 0 plus h, and this is this. That means in place of 0 plus h, that means more than 0. So more than 0, again the same function. In place of x I will put h. So here I put h. Okay, so and this is that h at the bottom. So it is coming out to be how much? E to the power minus this h and this h cuts. So e to the power minus 2 by h, and if I put 0, so 2 by 0 is infinity, e to the power infinity is 0. Anything to the power infinity is 0. So I see that the left hand derivative and the right hand derivative are not actually equal. So it is not differentiable. It is not differentiable at x equal to 0. Clear? Next, let's see the next sum. So the next sum shows that this is the function. We have to check at x equal to, we have to check the differentiability at x equal to a, and this is our function. So please see how to write it. If fx is differentiable, then we have to find the value of this. Fx is differentiable. So since fx is differentiable, so we can write this, definitely we can write like this. F dash a should be written as this, isn't it? Now in our original, this sum, in the sum, see what we are doing, we are adding minus a square fa and plus a square fa. Why we are doing that? Please watch here. In the first two I'll take fa common, so it is x square minus a square, and x square minus a square is a plus b into a minus b. So x minus a will cut, this will remain, okay, and this fa goes out. We have to apply the limit x tends to a in this part. Similarly, in the next part, if I take a minus common, and then if I take a square common, I will write like this. So a square goes out. Now this part is f dash a. This part is f dash a. Okay, and here if I put x tends to a, it becomes 2a. So this is our answer. fa into 2a minus a square f dash a. This is our answer. Let's see the next sum. For what value of a and b, the function this, we will take x square if it is less than or equal to c, and we will take ax plus b if it is greater than c, and I have to find the values of a and b, and they are telling it is differentiable at x equal to c. That means I have to check, I have to find out the left hand derivative. This is the left hand derivative at x equal to c. So I have to write limit x tends to c minus, x tends to c minus can be written as limit h tends to 0. In place of x I will put c minus h. In place of x I will put c minus h. So less than c, that means I have to choose the x square function. So in place of x I will put c minus h whole square minus c square, and this is c and c will cut, it is minus h. So now this part and this part will also get cancelled, take h common, so h cancels. Now in this part put h as 0, so we get plus 2c. Similarly, now I will check the right hand derivative. I will check the right hand derivative of the function. So x tends to c plus, that means I will take x, c plus h. In place of x I will put c plus h. In place of the x I will put c plus h, and h tends to 0. So more than c means I will now take ax plus b function, and in place of x I will put c plus h. So this is that x, and fc means in place of x put c. Okay, c and c cuts, it is h. Solving this we get a, Now they are telling it is differentiable. That means the left hand derivative and the right hand derivative should be same. The left hand derivative and the right hand derivative should be same. So 2c equal to a. Okay, so value of a is found. Now at x equal to c, at x equal to c, because it is differentiable, so it is continuous also. And for continuous, I have to find at x equal to c. So at x equal to c, the value is coming c square, and that also should be equal to the value at this, any of the left hand derivative, left hand or the right hand. So in place of a, I will put 2c, and so we can find out the value of b. So this is how, because it is differentiable, so it is continuous. I told you, because it is differentiable, so it should be continuous function. And for continuous, left hand derivative equal to right hand derivative equal to at x equal to c. At x equal to c, I will do all of the values should be equal. So at x equal to c, here we are putting the left hand derivative, this is the right hand derivative, equal to the value at x equal to c. So putting the value of a, I got the b. So next is, as you can see, f2 is given to us. f2 is this, f dash 2 is 1. We have to find the value of this. Okay, so see what we are doing. We are taking this function and we are just simply adjusting this. Okay, now from the first two parts I have taken f2 common outside. So in the bracket it remains x minus 2 by x minus 2. So this cuts, minus, in the second part I have taken 2 common. So this comes, and this is actually f dash 2. This is actually f dash 2. So here you can see. So it is f2, which is 4. F dash 2 is actually 1. So this is the value of this function. The value of this function is this. Now let us see the next sum. Discuss the differentiability of this function at x equal to 0. So we are now testing the left hand derivative. That means I will take less than 0. So less than 0, this is how I will write, and so it is x tends to 0 minus. So 0 minus is 0 minus h. In place of x, I will put 0 minus h. Okay, so it is minus h. Now if it is less than 0, this function will become x, and this is minus x, which is minus x square. And if it is more than 0, it will become x and x, which is x square. So for the left hand derivative, I will choose this function. So that is why, see, we are taking this, and we are, the h gets cancelled, we are getting h. So limit h tends to 0, h will be 0. Now testing the right hand derivative. So this is how we write the right hand derivative. As you all know how to write the right hand derivative, and in place of x, I will put, in place of x tends to, I will put 0 plus. So in place of x, I will put 0 plus h, 0 plus h. So it is h and h. And if I put h in place of x, the function comes out to be this. And if I put 0, it comes out to be 0. So this is h square, one h will cut, and mod h tends to 0 is 0. So see, left hand derivative is equal to right hand derivative at x equal to 0. So it is differentiable at x equal to 0. It is differentiable. Now friends, let's see the next sum. Discuss the continuity of the function and discuss the continuity and differentiability of this. So if it is less than 1, I will choose this equation. If it is more than or equal to 1, I will choose this equation. Okay. Similarly, if it is less than or equal to 2, I will choose this equation. And if it is more than 2, I will choose this equation. So there are two parts. I have to check at x equal to 1. That means at 1 minus 1 plus, and then I have to check at 2 minus and at 2 plus. 2 minus and 2 plus. So these are the two parts. First I have to check at 1 minus, 1 plus, 2 minus and 2 plus. Okay, so let's start with the 1 minus. So in place of x I will put, so here let us choose less than 1 is this function. Less than 1 is this function. I have to choose less than 1 and then putting the value of x. So less than 1, 1 minus, so in place of x, here I will put 1 minus h, and h tends to 0, so it comes out to be 0. Now 1 plus, so more than 1 I will choose this function, and in place of x I will put 1 plus h, 1 plus h, and it comes out to be this. So the value is this. Okay, so the left hand derivative and the right hand derivative, we are testing the limit. We are testing the limit. Okay, so the left hand limit, the right hand limit, and at x equal to 1, it is, we will put at this function, and it is coming out to be 0. So see, left hand limit, right hand limit, and x equal to 1, all the values came 0. So it is continuous at x equal to 1. It is continuous at x equal to 1. Now we will test the at x equal to 2. So for less than 2 I will choose this function, and in place of x I will put 2 minus h, h tends to 0. So we get 0. Right hand limit at x tends to 2 plus. So we will choose more than 2, we will choose this function, and in place of x I will put 2 plus h. We are getting this, and the value comes 1. So see, left hand limit and right hand limit are not equal, so it is not continuous at x equal to 2. It is not continuous at x equal to 2. Okay, and now we have to test the differentiability. We have to test the differentiability. We tested the continuity. We tested the continuity, and now we will test the differentiability of the function. So for differentiability at x less than 1, so we know that this is how we have to write, and for more than 1, right hand derivative, x tends to 1 plus, so we have to write like this. Okay, so less than 1 is less than 1 minus, and more than 1. So now see, in place of x I will put 1 minus h. Okay, so more, it is less than 1. So which function shall we choose? We will choose the first function, 1 minus x. we will choose the first function, and in place of x, so see 1 minus x, 1 minus, and in place of x I will put 1 minus h. Clear? And this is, in place of x I will put 1. So this is that, this. So function I have chosen is 1 minus x. On this function we are trying to test. So it comes out to be this, and it is minus 1. Now right hand derivative. So for right hand derivative, please watch. In place of x I will put 1 plus h. And which function shall I choose? I will choose this function. I will choose this function. 1 minus x into 2 minus x. Okay. So this is that 1 minus x, this is that 2 minus x. In place of x I will put 1 plus h, 1 plus h. And here I will put, in place of x is 1, 2 minus x, in place of x is 1. So we get minus 1. That means the left hand derivative is coming right hand derivative equal. That means I can say that it is differentiable. Sorry, it is differentiable at x equal to 1, but it was not continuous at x equal to 1. It was not continuous at x equal to 1. So let us test this function. Test the differentiability. First we tested the differentiability at x equal to 1. Now we will test the differentiability at x equal to 2. We will test the differentiability at x equal to 2. So let us write down the differentiability part. So this is that left hand derivative at x equal to 2. The left hand derivative at x equal to 2, which is 2 minus, and the right hand derivative at x equal to 2. The right hand derivative at x equal to 2. Okay, so here we are testing at less than 2, less than 2. So we will take 2 minus h. So less than 2, which function shall I choose? Which equation shall I choose? Less than 2, I will choose 1 minus x into 2 minus x. Okay. So here, in place of x, I will put 2 minus h. So I have chosen the equation as 1 minus x and 2 minus x, and in place of x I will put 2 minus h here, and here I will put, in place of x I will put 2. Okay, so then calculating it, cancelling out the common terms, we are getting 1. Similarly, right hand derivative at x equal to, so more than 2, more than 2, so 2 plus h. So more than 2, which equation shall I choose? I will choose 3 minus x. I will choose 3 minus x. So this is the equation which I will choose, and in place of x I will put 2 plus h here, and here I will put, in place of x, 2. So we are getting minus 1. So see, here it comes plus 1, here it comes minus 1. That means it is not differentiable. It is not differentiable at x equal to 2. It is not differentiable at x equal to 2. Okay, so let's see the next sum. So the next sum says that this is the function fx is x square plus 3x plus a, and it is applicable when it is equal to or less than 1, and this function when it is more than 1. And I have to check the differentiable. It is differentiable everywhere. That means it is differentiable at 1 also. Okay, so they are telling find a and b. Okay, so let's see. So first of all, we know that it is differentiable at x equal to 1. So this is the left hand derivative. This is our left hand derivative. Clear? Okay, and we are testing at less than 1. So in place of, so we will choose this function, and in place of x I will put 1 minus h. So choosing the first equation, this is my x. In place of x, I have put, and here in place of x I will put as 1. So this comes out, the common parts cut out, and here we'll take h common, that cuts out. Now we'll put h as 0, we'll get 5. So the right hand derivative at x equal to 1, that means I will write limit x tends to 1 plus, x tends to 1 plus. So here is that 1 plus, and in place of x I will put 1 plus h. Which function? This function, bx plus 2. So here is our bx plus 2, and here is that x. So solving it, we are cutting out the common parts, we get b. Now since it is derivable, since it is differentiable, so the left hand derivative should be equal to the right hand derivative. That means I can tell b is equal to 5. Now if it is differentiable, it is continuous also. That means at x equal to 1 also it exists. So at x equal to 1 we will choose this function, put x as 1. It is this, it is this. So its value should also be equal to the left hand derivative or the right hand derivative, any one of them. So choosing the left hand derivative, 4 plus a equal to 5, a equal to 1. Okay friends, so next, see the next sum. We have to test the differentiability of this function at x equal to 1. Okay, so left hand derivative at x less than 1. So if it is less than 1, our equation, this will become negative, this will become negative, and the equation will be taken as this. So we are actually testing left hand derivative at this. Okay, so limit x tends to 1 minus, that means we will choose, this is how we write, this is our function we have chosen, this is the left hand derivative, we have to write like this, and in place of 1 I will write 1 minus h, 1 minus h. Which function shall I choose? This function. So in place of x I will write 1 minus h, in place of x here I will write 1. So solving it, we get minus 2, and putting the value of h as 0 we get minus 2. Similarly, the right hand derivative we will write like this, and for the right hand derivative, what is our function? The first part will become positive, second part will become negative, and this is our function. That means whatever value we test, the answer is always coming. Here is coming, this is in place of x, so x cuts out, basically it comes 1. So greater than 1, the answer is coming actually how much? 1. So it is 1 plus h, and in place of, so this part also comes 1. Putting this value also I will get 1, this value also I will get 1, this value also I will get 1 and 1. So it comes 0, right? It comes 0. That means the left hand derivative is not equal to the right hand derivative, so it is not differentiable at x equal to 1. So friend, let's see the next sum. The next equation says that if you take more than 1, you have to take this equation, which is coming as 1. If you take less than 2, you have to take this equation. More than 1 or less than 2 is this equation. and more than 2 is this equation, which is actually 2x minus 3. So now let us test the differentiability at x, left hand derivative at x, so 2. So I am testing it at less than 2. I am testing it at less than 2. That means in place of x I will put 2 minus h. Okay, so we will less than 2, I will take the equation as 1. So putting 2 minus h also, I am getting 1. Putting 2 also, I will get 1. So this is 0. Now testing the right hand derivative at x equal to 2. This is our format to write. In place of x I will put 2 plus h, and I will choose the second equation. In place of x I will put 2 plus h. Here in place of x I will put 2. It comes out to be 2. Okay, now question is, left hand derivative is not equal to the right hand derivative x equal to 2, so it is not differentiable at x equal to 2. Now the next sum says this is our function, find f dash 3. That means I have to test the limit, the derivative at x equal to 3. So less than 3, left hand derivative less than 3. That means in place of x I will put 3 minus h. 3 minus h. So I will choose this equation, and in place of x I will put 3 minus h. 3 minus h, and here I will put, in place of x I will put 3. So solving it, we are getting this. Okay, so this is our f dash 3. This is our f dash 3. Next, if we see the next function, find f dash 2, f dash 5. This is the function given. That means we have to test the limit at 2 and 5. Okay, so let's check the left hand derivative at x equal to 2. So less than 2, less than 2, this is how we write. That means in place of x I will put 2 minus h. So in place of x I will put 2 minus h, and here in place of x I will put 2. Solving it, cutting out the common parts, we are getting this, taking h common, which cuts, and now putting the value of h is 0, which is coming as 11, because there is a minus here also. So f dash 2, because it is differentiable, so left hand derivatives value, whatever it comes, that is f dash 2. Now we have to test it at 5. So left hand derivative at 5, that means limit x tends to 5 minus. So in place of x I will put 5 minus h. So choosing this equation, I am putting 5 minus h, and here it is f5. So in place of x I will put 5. Calculating and cutting the common parts, taking h common, so it is minus 17, and putting h as 0, we get 17. So f dash 5 is coming 17. So friends, with this we complete the differentiability of the equations, and as I have told you that I have shown you how to do the differentiability of a given function. So my request is, please go through the things very, very carefully, because you have to understand that the application of the finding of the differentiability is very important. Okay, only when you go through it slowly and learn and practice with me, then only you will be able to understand it. So again, I am requesting, please keep following Parijat sir classes, because I am uploading all the important topics for you each and every day. So please go through it. Okay, this will help you for your board examinations. So please like, share and subscribe my channel. Okay, so thank you very much for watching this. Thanks a lot.